Picture the surface of the Arctic Ocean in deep winter. It isn't water. It's a solid white plain stretching past the horizon in every direction. Frozen concrete, several stories thick, locked together for hundreds of miles. Now picture a ship driving straight into it. Not slowing down, not turning away. A vessel weighing 30,000 tons, aiming itself directly at ice that could hold the weight of a city, and somehow coming out the other side, leaving a clean channel of open black water behind it. So how does that actually happen? Does the ship just hit the ice harder than the ice can resist? Is the bow some kind of giant blade? And how does a hull made of steel survive doing this over and over for an entire winter without tearing itself apart? Here's the part that flips the whole thing around. The ship you're picturing isn't smashing through that ice at all. It's doing something far stranger. And once you see it, you'll never look at an icebreaker the same way again. Let's start with the mental image you're carrying, because it's wrong. Most people imagine an icebreaker as a battering ram, a heavy pointed bow charging forward, slamming into the ice edge, punching a hole through sheer force. Crash, crack, repeat. That picture makes sense. It's just not how it works. A wall of ice 10 feet thick is astonishingly strong when you push against its edge. Hitting it head-on is like throwing your fist at the side of a brick. The ice barely notices. The ship loses. So an icebreaker doesn't attack the ice from the side. It attacks it from above. Here's the secret hiding in plain sight. Look at the front of a real icebreaker, and you'll notice the bow isn't sharp and vertical like a knife. It's sloped, rounded. It angles backward and upward, almost like the curved front of a sled. That shape is the entire trick. The ship doesn't drive into the ice, it drives up onto it. The sloped bow slides over the leading edge of the ice sheet, and the front of this enormous vessel physically lifts out of the water and climbs on top of the frozen surface. And now the ice isn't being punched, it's being sat on. Think about the difference between trying to punch through a dry cracker held at the edge versus laying that cracker flat and pressing down on it with a knife. The edge resists you, the flat surface snaps instantly. Ice behaves exactly the same way. It's tremendously strong against a sideways shove and surprisingly weak against a downward press. An icebreaker is a machine built entirely around exploiting that one weakness. So let's walk through a single cycle of braking, step by step, the way it actually unfolds out on the ice. The ship approaches the unbroken sheet at a slow, steady pace, just a few miles per hour. This is not about speed. The sloped bow makes contact and begins to ride up. The reinforced steel of the forward hull slides over the ice edge, and the entire front of the ship starts rising. For a moment, thousands of tons of bow are no longer floating. They're suspended in the air, balanced on top of the ice sheet, held up only by the strength of the frozen surface beneath. And the ice cannot hold it. Gravity takes over. The full downward weight of that lifted bow drives straight through the sheet. The ice fractures, and a slab the size of a parking lot cracks free and plunges underwater. Imagine dropping a fully loaded cement truck onto a frozen pond. That's the kind of concentrated downward force happening at the bow of an icebreaker, over and over, every few seconds. The ship settles forward into the gap it just made. The broken slabs roll and tumble beneath the hull, and the sloped bow finds the next edge of unbroken ice and starts climbing again. Climb. Press. Crack. Settle. Climb again. That's the rhythm. An icebreaker moving through a thick flow isn't charging. It's a slow, relentless cycle of lifting itself up and letting its own weight do the destruction. The engines aren't there to provide a punch. They're there to keep shoving that sloped bow up onto the next sheet. And those engines are monsters. A large nuclear icebreaker can put out more than 70,000 horsepower. That's the combined output of roughly 500 ordinary cars, all of it funneled into a few enormous propellers turning under the ice. Those propellers matter more than you'd think. They're built from thick cast steel, and the blades are often designed to be unbolted and replaced one at a time, because chunks of ice sucked under the hull will chip and crack them. The propeller wash also does a second job. It blasts broken ice backward and away from the stern, helping flush the channel clear so it doesn't simply freeze shut again behind the ship. Now here's the part that genuinely defies common sense. Sometimes the ice is simply too thick for that steady rhythm to work. Pressure ridges, where two ice sheets have collided and buckled, can pile up far thicker than the surrounding flow. The ship rides up, presses down, and the ice doesn't break. So what does the ship do? It goes backward. The icebreaker stops, reverses several ship lengths back into the channel it already cleared, and then drives forward at full power to slam into the ridge and ride as far up onto it as possible. Then it backs up and does it again. And again. It's called backing and ramming. The strongest ships on Earth, defeating the hardest ice on Earth by repeatedly retreating. It's like needing to reverse your car down the driveway just to get a running start at a snowbank. And it gets stranger. The most powerful icebreakers are deliberately built wider than the cargo ships they escort, because the channel has to be wide enough for those ships to follow without scraping. And some modern icebreakers are designed to break ice while traveling backward, using a specially shaped stern, because in certain conditions going in reverse clears a better path than going forward. A ship engineered to work best while moving in the wrong direction. That's how upside down this field gets. So how does the hull survive all of this without being shredded? This is where the hidden engineering lives. The hull of a true icebreaker is not a normal ship's hull. Around the waterline, where the steel meets the ice, the plating is enormously thick. We're talking steel several inches deep, layered like stacking multiple car hoods together into one solid wall. Behind that outer skin sits a second inner hull, a double wall. If the ice ever tears the outside open, the inside still keeps the ocean out. The hull is also rounded underneath, with no sharp lower edges for the ice to grab. This shape matters for a reason most people never consider. If an icebreaker ever gets trapped in ice, squeezing it from both sides, that rounded hull means the pressure pushes the ship up instead of crushing it inward. The vessel pops upward, like a wet watermelon seed shooting out from between two fingers, rather than being slowly flattened. And then there's the problem of friction. Broken ice scraping along the steel sides slows the ship dramatically. So many icebreakers carry a system that blows compressed air out through holes below the waterline, wrapping the hull in a curtain of rising bubbles. Some use jets of water instead. Either way, the ice is lubricated, so it slides past the steel instead of gripping it. The hull becomes a wet bar of soap, and the ice just slips off. Some ships go one step further. They carry tanks of water on either side and pump it rapidly from one side to the other, deliberately rocking the entire vessel back and forth. That rolling motion widens the channel and shakes loose ice that's clinging to the hull. A 30,000-ton ship, intentionally wobbling itself free. None of this was figured out overnight. The first real icebreakers appeared more than 100 years ago, and the slope bow was the breakthrough that changed everything. Before that, ships just rammed the ice and hoped. Every shape you see on a modern hull was earned through decades of vessels getting stuck, getting crushed, and getting redesigned. Here's why all of this matters far beyond the Arctic. You've never seen an icebreaker. You've almost certainly benefited from one anyway. Northern cities and remote settlements rely on ships for fuel, food, and supplies. And in winter, the sea route to reach them freezes solid. An icebreaker goes first, carving a channel, and the supply ships follow single file in the open water behind it. It's a snowplow clearing a lane on a highway, so the cars behind can finally move. The frozen ports of the far north stay open through winter, only because icebreakers keep grinding their channels open. The research vessels studying climate at the top of the world get there on icebreaking hulls. The natural gas and oil that flows out of Arctic terminals reaches the rest of the planet on tankers that an icebreaker cleared the way for. Whole economies sit on top of this. The price of heating fuel in an Arctic town in February quietly includes the cost of a ship that spent days breaking a path to deliver it. But this system has a brutal, honest cost. Icebreaking is painfully slow. A ship that crosses an ocean of open water in days can spend that same time crawling through a single, difficult stretch of heavy ice. It is one of the most fuel-hungry jobs in all of shipping. Hours of straining engines to travel a distance you could walk. And it is not guaranteed to work. A ship can get beset. That's the term for being frozen in place when the surrounding ice closes in and locks the vessel solid. The pressure of ice sheets driven together by wind and current can be immense. A 30,000-ton ship, one of the most powerful machines humans have ever floated, can be held completely motionless by nothing but frozen water pressing on its sides. Crews have been trapped like this for days, waiting for the wind to shift and the ice to loosen its grip. In the worst cases of the past, ships caught this way were slowly crushed and lost entirely. The ice always gets a vote. So here's where you land after all of this. You started out picturing a battering ram, a ship that wins by hitting harder, brute force against a frozen wall. What's really out there is something much smarter, a machine that refuses to fight the ice on the ice's strongest terms. It climbs instead of charges. It turns its own enormous weight into a downward blade. It lifts itself up just so gravity can do the braking for free. It's not strength against the ice. It's geometry against the ice. Next time you see footage of one of these ships carving a black channel across a white horizon, you'll know it isn't smashing anything. It's climbing, pressing, and falling, thousands of tons at a time. But breaking ice from above is only half of the story, because there's another machine that solves the exact opposite problem. A submarine sitting in the black water beneath that same ice that needs to get to the surface, with 10 feet of frozen ocean sealing it in from above. How a vessel punches up through Arctic ice from underneath is a completely different physics problem.